Hello and welcome to this A-level chemistry explanation video about the halogens. That is the green column in the periodic table for group 7. I'm going to be taking a look at the physical properties of the group 7 elements, specifically focusing on electronegativity and boiling point. From there, we're going to look at the chemical reactions of the halogens. This will include how we test for the presence of halide ions, how we can prove the oxidizing ability of the halogens, and the reducing ability of the halide ions. And we'll also take a look at how we can use some of these group 7 elements to purify our drinking water and produce cleaning products such as bleach. You need to know about some of the properties and physical trends of the group 7 elements. The first thing that we should consider when we're talking about the group 7 elements is that they are diatomic molecules. That means that they are covalently bonded and that there are 2 atoms per molecule. Then we need to consider the fact that these molecules are different. First of all, they look different. Fluorine is a pale yellow colour, chlorine is more green, bromine is a reddy brown colour, and iodine is grey. Not only do these molecules differ in colour, they also differ in size. Fluorine is a very small atom, so the fluorine molecule is the smallest of the halogens, and then chlorine is slightly larger, then bromine, and then iodine. This gives rise to a number of physical properties. The first physical property that we're going to look at is electronegativity. Now, the electronegativity is the ability of an atom to attract electrons from a covalent bond. And so this is determined by the strength of the electrostatic attraction between the positive nucleus and that covalently bonded electron pair. Now, since the atoms get larger as you go down group 7, there is a bigger distance between the nucleus and the covalently bonded electrons, and there are also energy levels between these covalently bonded electrons and the nucleus, more so as we go down the group. As a result of this, the electronegativity decreases down the group because that electrostatic attraction between the nucleus and the covalently bonded electrons decreases. You need to know that the boiling point of the halogens increases as we work our way down group 7. This is because halogens are diatomic molecules and they get larger as we work our way down the group. Now, since they are molecules, what holds these molecules to each other is intermolecular forces, forces between the molecules. Now, there are 3 types of intermolecular force, but only one of them is present in the halogens. And that's because all of the elements within a particular sample of a halogen are all going to be the same. They're all going to be bromine, for instance. And so all of the electronegativities will be the same, so there won't be any dipoles. And so the only force will be van der Waals forces, which is a temporary dipole inducing a dipole in a neighbour. Now, the van der Waals forces get stronger as the number of electrons in a molecule increases or as the molecule size increases. And so, because chlorine is bigger than fluorine, chlorine will have a higher boiling point than fluorine because it's going to have stronger van der Waals forces. And that trend will continue as we work our way down the group. And so we need to know fluorine, chlorine, bromine, and iodine. And we need to know that because they show an interesting pattern that fluorine and chlorine have such weak van der Waals forces that their boiling point is very, very low. And so they are actually gases at room temperature. And so that means that there is enough energy to melt and then boil these gases just at room temperature. Whereas bromine is a bit more large as a molecule and therefore has stronger van der Waals forces, and so the boiling point of bromine is above room temperature. So that means at room temperature, bromine doesn't have enough energy to overcome the van der Waals forces between the liquid bromine molecules. And then we move on to iodine. Iodine is much larger still, which means stronger van der Waals forces still, and so much so that the melting point of iodine is actually above room temperature. And so iodine is actually a solid at room temperature because there's not enough energy in the iodine molecules to break away from their lattice structure that they have as a solid. Typically, we aren't asked questions about astatine in A-level chemistry, but we could be, and we would expect this pattern in boiling point to continue, and therefore we would expect astatine to have a higher melting point than iodine, and so be a solid at room temperature. There are a number of chemical reactions that we need to know about for the group 7 elements, one of which is the oxidizing ability of the halogens. Now, oxidation is the loss of electrons and reduction is the gaining of electrons. So the ability of an atom to oxidize another atom is effectively saying how good is that atom at taking electrons away from something else, because it's causing the oxidation of another substance. And so an oxidizing agent actually accepts electrons from another substance, thereby making that substance lose electrons. The oxidizing ability of the halogens follows a similar pattern to the electronegativity of the halogens for almost the same reasons. So if oxidizing ability is the ability of an element to take electrons from something else, that ability is going to depend on the attraction from the nucleus for that atom for the extra electron or electrons that it is going to be trying to gain. And so as we work our way down group 7, the elements will get larger, and as a result of that, the shielding will increase, and the distance between the nucleus of that atom and the electrons that are being gained will be increasing as well. So there will be a weaker attraction for those electrons that are potentially being gained, and so that electron will be gained less easily, and so that substance will not be such a good oxidizing agent. It won't be able to take electrons from other things so well. And so as a result, fluorine is going to be the best oxidizing agent of group 7, then chlorine, then bromine, then iodine. Now, of course, we don't typically get asked about astatine, but we could be, and we would expect that pattern to continue. We can prove the pattern in oxidizing ability of the halogens by looking at displacement reactions, which you learn about in GCSE chemistry, and you learn it from the point of view of a more reactive substance taking the place of a less reactive substance in a compound, but in A-level chemistry we need to consider these to be redox reactions, where the more reactive halogen is actually going to be taking electrons from the less reactive halogen, or specifically halide ion. And so what you would do is you would add chlorine water, so that means Cl2 dissolved in water, to substances of, say, sodium chloride, sodium bromide, sodium iodide, each of which starts colourless. And we would expect chlorine to be the best oxidizing agent of the three that are being used. And so what we would expect is the chlorine to be able to oxidize bromide and iodide ions. And that's what happens. What we would see is we'd see the orangey yellow color of the bromine appearing, and that would tell us that the bromide has been displaced, but more specifically that the bromide has been oxidized. And with the iodide, we would expect to see a brown solution forming, and that would be iodine that had been formed through the oxidation of the iodide ions. And so in terms of redox, what happens is the Cl2 molecules will turn into Cl- ions as a result of gaining electrons from the other halide ion, the bromide or the iodide, and then the bromide ion would do the opposite. We would have Br- turning into Br2. We need to show the electrons gained by the chlorine by having them on the left-hand side, and we need to show the electrons being lost by the bromide by having them on the right-hand side. And the overall equation is found by adding the two half equations together, the one for the reduction and the one for the oxidation. And then what we do is we simplify this overall equation by getting rid of the electrons that are present on both sides, and so therefore can be considered to not be changing, and so shouldn't be included. The equation is really, really similar for the iodide oxidation. Iodide turns into iodine, and we have two electrons on the left-hand side. And so the overall equation for the formation of that brown solution is really, really similar to the orange solution for bromine. And then we could do the same thing by adding bromine water to the same three samples, sodium chloride, sodium bromide, sodium iodide. We wouldn't expect anything to happen for sodium chloride or sodium bromide, but we would expect the brown solution again to form for potassium iodide for the same reason. The iodide gets oxidized to I2 and the bromine would get reduced to Br-, and so these two half equations would combine to give the overall equation that looks really similar to the situation for chlorine. And so what we've proven so far is that chlorine is a better oxidizing agent than both bromide and iodide, and Br2 is a better oxidizing agent than the iodine. And we would finish this off by reacting iodine solution with sodium chloride, sodium bromide and sodium iodide, and we would expect no reactions to occur because iodine is not a very good oxidizing agent. A number of the chemical reactions of the halogens are specific to chlorine, the first of which is making bleach. Now, if you mix chlorine with dilute sodium hydroxide solution at room temperature, so it's quite cold, what you end up producing is sodium chlorate 1 solution and sodium chloride and water. The sodium chlorate 1 is household bleach, which is used to kill bacteria. Now, specifically, it's the chlorate 1 ion that is able to kill the bacteria. This is an interesting type of reaction known as a disproportionation reaction. And in a disproportionation reaction, what happens is one substance is oxidized and reduced simultaneously. If we take a look at the overall equation for this, we can see that the sodium hydroxide, two of them, are reacting with the chlorine. Now, chlorine is a diatomic molecule, but both of the atoms in the element chlorine have got an oxidation state of 0. All elements have an oxidation state of 0. So this is at the beginning of the reaction. Now, if we look at the two chlorine-containing products, the sodium chlorate 1 product, first of all, sodium has an oxidation state of +1 because it is from group 1, and oxygen is -2 because it's from group 6, which means that the sodium plus the chlorine plus the oxygen is adding up to the 0 that this overall substance has got for its charge, and so that means that chlorine's oxidation state must be +1. And that means that one of the atoms of chlorine at the beginning has gone from 0 to +1, so it has been oxidized. And the other product that contains chlorine is sodium chloride, which is a more simple calculation. Sodium is +1, the chlorine must be -1 because overall it is 0. So this atom of chlorine has been reduced. It has gained 1 electron. So within the chlorine molecule, one of them has gained an electron and the other one has been lost. And this is called a disproportionation reaction. Those two chlorine atoms have had a disproportionate share of those electrons. One of them has taken more than the other and the other one has lost. Now, sodium chlorate 1 is used in bleach, but it's also good for other cleaning products as well, and also for preparing paper and other textiles. Bacteria in fresh water and drinking water can sadly cause many different diseases, and an epidemic of cholera, for instance, could end up killing thousands of people. And we use chlorine to overcome that by reacting chlorine with water and producing a chemical that is going to kill the bacteria and prevent humans from getting these diseases. Not only does it kill bacteria, it also prevents the growth of algae and thus eliminating bad taste from the water and removing any discoloration that could end up affecting the quality of our drinking water. This reaction is a disproportionation reaction, and that means that the chlorine in our reactant is both oxidized and reduced. Chlorine, the element, has an oxidation state of 0, and so that means that we've got two chlorine atoms starting with an oxidation state of 0. And so what we do when this reacts with water is we end up with an equilibrium, so this reaction is reversible, and we end up producing HCl, which in fact would be two separate ions, hydrogen ions and chloride ions, and we end up producing chlorate 1 acid, so that would be HClO. In HCl, the chloride's oxidation state is -1, and in the HClO, hydrogen is +1, oxygen is -2, so that means that the chlorine must be +1 because overall the oxidation state of this is 0. And it's this chloric 1 acid, or more specifically the chlorate 1 ion, that is able to kill the bacteria and therefore prevent us from getting ill. Now, as I've said, this has huge health benefits and prevents many people from getting ill, but it is not without its drawbacks. Chlorine as a gas can severely irritate the respiratory system. As a liquid, it can cause chemical burns and cause eyes and skin to itch. And in some cases, it can form chemicals that can prove fatal. And this is very, very, very small risk, and by no means certain that anybody's going to have any kind of reaction. And what we can absolutely say is that the small risk of an adverse response to this chlorine is definitely worth the benefit of preventing thousands and thousands of deaths from a cholera epidemic. Now, we have to make sure that the chlorine does not get exposed to sunlight whilst it's reacting with water, because if it does, we actually get a different chemical reaction occurring. The chlorine will actually not undergo the disproportionation reaction. It will simply form hydrochloric acid and oxygen gas. And so this does not produce our chlorate 1 ions that we need to kill bacteria. So we need to make sure that chlorine is added to the water away from direct sunlight. Otherwise, we won't get the benefit. Whilst the halogen molecules have got distinctive colours that darken as we work our way down group 7, the halide ions are all colourless, and so it could be impossible to distinguish between them just by simply looking at them. And so we need to know about a chemical technique that you can use to test for the presence of halide ions. The reagents that we use for this are acidified silver nitrate solution. Specifically, we acidify our silver nitrate by using dilute nitric acid. When you add the silver nitrate to our suspected halide ion, what you get is a product of silver halide being produced. Now, silver halides are nearly all insoluble in water, with the exception of silver fluoride. We don't get any visible change when we add silver nitrate to sodium fluoride solution, so we can't prove the presence of the fluoride ions. But we can prove the presence of the other halide ions because we get a precipitate forming. That means a solid that will not dissolve in the water that is present. And so if you add silver nitrate to a substance that contains the chloride ions, so for instance sodium chloride, we will see a white precipitate forming. And the bromide ions would give a cream precipitate, and the iodide ions would give a yellow precipitate. The reason for this is that the silver ions in silver nitrate react with the chloride ions to produce silver chloride. Silver chloride is insoluble in water, and so that is the identity of the white precipitate. Similarly, the cream precipitate is silver bromide that's formed in this reaction. And then the silver iodide forms, that's the yellow precipitate, and this is the ionic equation for the formation of that precipitate. The reason that we add the nitric acid in the first instance is that there are often impurities in substances, and these impurities can react with the silver and typically produce white precipitates, and that can lead to misleading results that make us think that the chloride ion is present when in fact it's not. The most common impurity is the carbonate ion, and what happens is the hydrogen ions from the nitric acid react with this carbonate ion and turn into carbon dioxide and water. And so if that impurity is present, you might see a small quantity of effervescence, but it's unlikely to be loads of this carbonate impurity being present. And so once the carbonate impurity has reacted, it won't be there to react with the silver, and so we can be confident that any white precipitate that we see is down to the presence of the chloride ion, not a different impurity. The three precipitates that form after you've added silver nitrate to a solution containing a halide ion are not always easy to tell apart. The yellow precipitate for silver iodide is quite distinctive, but if you're only making one precipitate, it can be quite difficult to know whether what you've made is a white precipitate or whether it is a cream precipitate, and so a follow-up test is needed to prove one way or the other. The chemical that we use to do this is ammonia solution. Dilute ammonia solution is first added to your test tube containing your precipitate. After you give it a bit of a swirl around, that precipitate will dissolve and therefore go back to being a colourless solution if that precipitate was the white silver chloride precipitate. If it was the cream silver bromide precipitate, that precipitate will remain. In other words, it won't dissolve in this dilute ammonia. And that allows us to be confident that the precipitate was or wasn't silver chloride. And then we can be doubly sure, if we don't get that precipitate dissolving in the first instance, that the precipitate was silver bromide by adding concentrated ammonia solution to the bromide precipitate. Because when you add concentrated ammonia solution, that silver bromide will fully redissolve in a way that it wouldn't for the diluted ammonia solution. And then if the precipitate stays after the addition of concentrated ammonia solution, we can be totally confident that it was the iodide precipitate, silver iodide, that had formed in the first instance. This can be particularly useful if we had a mixture of different precipitates forming after the addition of the silver nitrate. We could have had chloride ions present and we could have had iodide ions present, and so what we might have formed was a precipitate that was a mixture of the white silver chloride and the yellow silver iodide. And so after the addition of the dilute ammonia solution, the precipitate might have gone yellow because the white aspect of that precipitate would have redissolved. And then after we add the concentrated ammonia, nothing further would change, thereby proving that we had the mixture of silver chloride and silver iodide in the first instance. As an extra area of interest, the redissolved solution actually makes something quite different to what we started with. When you have the ammonia added to the silver chloride, for instance, what we end up making is a complex ion that contains silver and 2 ammonia ligands, and it looks like this. This is actually the active ingredient of Tollen's reagent that you can be using to differentiate between an aldehyde and a ketone. It's the chemical that gives us the silver mirror with the aldehyde, but does nothing with the ketone. No visible change there. We can carry out chemical reactions in order to prove the pattern in reducing power of the halide ions as we work our way down group 7. Reducing power is the ability of an atom or ion to cause the reduction of another element. And so reduction is the gaining of electrons, so reducing agents donate electrons to other substances. And so the reducing power of the halide ion will be determined by its ability to lose its own electrons and thereby donate them to something else. And so since the halide ions get larger as we work our way down group 7, the outer electrons of the ion are going to end up being further from the nucleus, and they're going to be shielded from the nucleus's attraction, so they're going to be experiencing a weaker electrostatic attraction from that nucleus for those electrons in the outermost energy level. And so as a result of that, the electrons are going to be lost more easily, and so therefore you would expect the halide ions to get better reducing agents as we work our way down group 7. Their reducing power will increase. We can prove the pattern in reducing ability of the halide ions by reacting those ions with concentrated sulfuric acid. What we do is we take a solid sample of our halide ion, so for instance sodium chloride, sodium bromide, sodium iodide, and we add sulfuric acid to it. Now what will happen in each case is there will be a chemical reaction occurring where the sulfuric acid reacts with the halide ion and we produce sodium hydrogen sulfate and a hydrogen halide as a byproduct. So something like hydrogen chloride, hydrogen bromide, or hydrogen iodide. This isn't a redox reaction, and we can prove that by showing that the sulfuric acid contains sulfur with an oxidation state of +6 at the beginning, because hydrogen is +1, +1, and then -2, -2, -2, -2 from those 4 oxygens, so the sulfur must be +6. And then we've got the exact same situation for the sulfur in the products. The only difference is that the positives are coming from 1 sodium and 1 hydrogen this time, but they're both +1 each. So this isn't redox, the sulfur has not changed its oxidation state. And so in this instance, the sulfuric acid is just simply acting as an acid and donating a proton to the halide ion. And this hydrogen halide would float away from our reaction mixture, and we could prove that it was there because we could hold, say, for instance, a glass rod with a drop of ammonia solution on the end of it, and that would form a white solid of the ammonium chloride or ammonium bromide or ammonium iodide, and we would be proving the presence of this hydrogen halide through this method. But this is not always necessary to do because you would expect to make some hydrogen halide for each of these reactions, whichever halide ion you were using. And in fact, for the sodium chloride in this example, this is all you would expect to see, because chloride ions, being so small, are very poor reducing agents. Chloride holds onto its electrons too tightly for something like sulfur to come along and take them away, and that's why reduction doesn't take place of the sulfur in this instance, and the chloride remains as Cl- and no redox occurs. For the bromide and the iodide, we do get redox reactions occurring, and what happens to the halide ion in general is that they give away electrons and they form their element. So we're showing this with X- turning into X2 and 2 electrons. That's the general rule. But for bromide, of course, we make Br2 with 2 electrons, and for iodide we make I2 and 2 electrons. In the reaction with sodium bromide solid then, if we're making bromine as a product, we will see that because we'll get orange fumes forming of the Br2. We will also reduce the sulfur in the sulfate ion and produce sulfur dioxide gas, which is often described as choking fumes of sulfur dioxide. We can actually test for sulfur dioxide by holding some potassium dichromate paper over it, and that will change from orange to green, proving that we've made sulfur dioxide. The half equation for the formation of sulfur dioxide has got SO4 2- turning into SO2 gas. To balance this half equation, we need to first check for our atoms that aren't oxygen or hydrogen, and we are balanced already for that with the sulfur. Then we need to add 2 water molecules to the right-hand side to balance for our oxygen. Now we've added 4 hydrogen atoms on the right-hand side, so we need to add 4H+ to the left-hand side. And then we need to look at charges. The left-hand side has got a charge of +2 overall. The right-hand side has got a charge of 0 overall, so we need to add 2 electrons to the left-hand side to make neutral on both sides. When we combine that with the bromide half equation, we can see that the bromide are losing 2 electrons and the sulfur is gaining 2 electrons, so we combine these in a 1-to-1 ratio. And so overall, the redox equation looks like this, and we can actually show it as a non-ionic form because we can represent it as the hydrogen bromide gas that has been produced as reacting with the sulfuric acid in its undissociated form to make the Br2 and the sulfur dioxide and the water. Either of these is fine, in ionic format or just as full molecules with no charges being shown. The iodide ion is such a good reducing agent, it is actually able to reduce the sulfur to produce 3 different sulfur-containing products, each of which have been reduced from the initial +6 oxidation state. It's able to react in the exact same way that the bromide does, so producing sulfur dioxide and water and iodine. The iodine that we see will either be a solid iodine, so that therefore it will look like a grey solid, or the exothermic nature of this reaction might be strong enough to produce some gas, so we might see purple gas being produced instead. So either of those observations could be made in this situation. So that's the same as the bromide ions, but iodide is a better reducing agent. It's actually able to reduce the sulfur to make solid sulfur, which has got an oxidation state of 0. So this time we've gone from +6 oxidation state in the sulfur to 0 oxidation state. So that means that the iodide is able to force the sulfur to gain 6 electrons. And also it can in fact make hydrogen sulfide. In hydrogen sulfide, the sulfur has actually got an oxidation state of -2 because each of those hydrogens is +1. And so that means that the sulfur in the sulfate ion has gone from +6 to -2, therefore it must have gained 8 electrons in the process. That's how strong a reducing agent iodide ions are. They are able to force the sulfur to gain a total of 8 electrons through their reduction reaction. And so the half equation for this would have the sulfate ion on the left and hydrogen sulfide on the right. We would need to balance for oxygen by adding 4 water molecules to the right hand side, and then we would need to add a total of 10 hydrogen on the left hand side. And then you can see that we need to add 8 electrons to the left hand side to balance the charge and give us our overall reduction half equation. And so the iodide, which only needs to lose 2 electrons per 2 iodides, making iodine, we can see that we need to multiply that half equation by 4, and then when we combine it together, we simplify out the electrons, and we get an overall redox equation of this. Now, this reduction can actually take place sequentially, so that means that we might not necessarily reduce the sulfur all the way in one go from +6 to -2. We might first reduce that sulfur from +6 to +4 in the SO2 molecule, and then that SO2 molecule might then be reduced further to make hydrogen sulfide, for instance, along with the solid iodine. And so you need to be able to construct these half equations from the situation that you're given, rather than memorizing them and just expecting to be able to retrieve them in a test. It is far better to have that flexibility to be able to work out the half equations and then combine them to give a full overall equation, depending on the situation. Okay, that's the end of this explanation video about the group 7 elements and their reactions. I hope it was useful. I'll see you again soon.